So that's basically how we locate the centroid, which is fairly important. The next concept we'll be talking about is the moment of inertia, or the second moment of area. So the second moment of inertia, it increases with the size of the object. But it also increases with having distribution away from the centroid. The definition of how we calculate that is we're basically using x squared. It's x squared dA integrated over the area instead of x dA like we saw with the centroid with the first moment. That's what we call it. That's why it's also sometimes called the second moment of area. And for this again, we don't divide by the integral of the dA over the area as well. This stays in this. So its units are going to end up, once we integrate the dA, in units of length to the fourth. So another thing to note here is that it is only the distance away from the axis that you're looking at that matters. So I'm just going to go ahead here, just get your quick axes. So if we take this shape here and kind of shift it over, cut this section off here and move it to the other side so that we get this shape here. If we're calculating our IX, so our moment of inertia about the x-axis, you'll note that none of these terms, other than the dA portion, it would just be the size of the little cubes. So those would have some x component to them, but they don't vary. They just provide the location of that area that you're looking at. They don't vary with the x otherwise. So if you integrate if you integrate y squared dA for this shape, it would be the exact same as if you integrate y squared dA for this shape. Actually, even if we use the same reference point, reference system, even if our 0 was still over here, shifting the same object to the side also does not change your ix. It would change your iy, obviously, because there we're worried about the x squared, x squared dA. So either changing this shape to this shape is going to change your is going to change your IY, or just taking this thing and shifting it to the left or shifting it to the right is also going to change your IY. So location and distribution away from the centroid. So taking something and shifting it away from the centroid. Changes things. Shifting it away from the axes that you're taking the moment about also changes it. We've also got this thing, the polar moment of inertia. So this is basically working off a perpendicular distance instead of a linear distance. So we're working from a reference point here, and we're taking the radius from our reference point to the little dA squares. So obviously for this one, moving the object up or down in the x or y directions will change the polar moment of inertia, and as well as changing the distribution of the object itself. So again, that once you kind of run the math, actually works out that the polar moment of inertia, that's just Ix plus Iy. I'm sure that those of you who are keeners could go ahead and plug those equations together and verify that that's the case. I'm not going to bother spending 20 minutes trying to work through any math on that. You can take it on my word if you want. Sometimes it is denoted as IZ, so basically a moment of inertia about the z-axis instead of J or J naught. Again, Wikipedia uses that. Our textbook uses J. I'm gonna stick with J for this course, but yeah, just keep that in mind that may be the case if you're trying to find your references otherwise. So if you're wondering why we're worried about these, generally speaking, we're worried about these because the moments of inertia kind of allow us to figure out how an object will, or like say a beam, will respond if we try to bend them about the x-axis or about the y-axis. So it'll determine, it determines stuff like how much it bends, like how much curvature you get, and it also help determine your stress distribution there. So those are both critical. One thing to keep in mind is that oftentimes when you're looking at the cross sections, you need to keep in mind that your axes need to be consistent, because especially oftentimes when if we're just looking at a cross section, we're often going to be defining x and y in terms of looking directly at the cross section and have z in and out of the plane. Oftentimes with our beam bending problems, we often define x as going along the beam, y is being vertical, and then z would be kind of in and out of the kind of acting perpendicular to both these axes. So if we're looking at a cross section, we'd need to kind of redefine our axes such that we would. I'm gonna reuse this one here. But if we're using these axes here for our beam problem, and then we sliced off the beam and we're looking straight at it. In this instance, we would actually have a scenario where again our y would be going in that direction, our z would actually be going in this direction. I tried to do here. So we wouldn't be using that at all. Our z would be going in that direction, and our x would be going in that direction. And again, that's just based upon that orientation. Again, is still just going to be based upon us having the right-hand rule in place. So in this instance, this is if we slice the beam off and we're looking at it from the positive x direction. So we're looking, if we take a slice. Why does this not let me draw? I want to draw, not move. So we take a slice here and we're looking at it from here. So just keep in mind you do need to at least keep your axes oriented the same way as anytime whenever you're doing your example problems. So we got this thing we call the parallel axis theorem. This basically allows us to work with, if we know what the moment of inertia for a particular shape is about its with the axes located at its own centroid, then we can figure out what the moment of inertia for that object about an arbitrary axis would be. So basically, if we've got a circle here, a circular cross section here, and then we got our x-axis here, our y-axis here, this would be what allows us to calculate the moment of inertia for an equivalent sized and shaped object, an equivalent circle. Let's assume that these both actually look like circles, about a set of axes that isn't located at its own centroid. Essentially, the way it works out is that you basically just take the initial x that you solved for, and then you add to it the total area times the shift in y. So in this instance, times the shift in y squared. So in this instance, dy would be here. So distance y, distance x would be here. So shifting left, shifting upward. Same deal as if you work as if you shift downwards, or shifting right, shifting upward. Same deal as if you shift downwards. Same deal as if you shift rightwards, because again, that term there is squared. So even if our distance in y or distance in x happens to be a negative value, it doesn't matter. It works out to the same thing. So we can take that, and we can essentially recalculate our terms based upon already having the known iy or the known ix for the original object and the shifted object. Same thing works for our j. I wanted to shift that. I didn't want to move it. And again, that shouldn't be too surprising, because we know that we know that in this instance we're just this value, these values here are just going to be these values plus these values. So the JC, the J bar C here is just the IX prime and the IY prime, and then our AD here, our AD squared, that just ends up being our AD squared just ends up being A times, again, our dy squared plus our d squared term here ends up just being A times our ax squared plus ay squared, because again, that's just Pythagoras' theorem. Dy dx d. How do we calculate d? We calculate it by square root of dx squared plus dy squared. Square both terms, and we just end up adding those things together. So why might we want to be doing that? Basically, it allows us to calculate what these things are for composite areas, stuff that isn't made out of stuff that is made out of a combination of relatively simple shapes, and you can use it allows you to recalculate the allows you to recalculate the new moment of inertia for the composite areas based upon the known initial moment of inertia for what you started with. So for in this instance, Ix, you'd basically just sum up the Ix prime for sum up the Ix prime plus the A dy squared prime for each of these two rectangular shapes that you're building. So Ix prime in this instance would just be the Ix calculated based upon having a rectangular shape, and the A is obviously just base times height, and then the dy prime in this instance would be calculated based upon the distance between the centroid here of the original built-up of the original rectangular member that kind of got added here, and the new centroid calculated based upon the combination of these two members in question. So that'd be for our Ix. In this instance, so this is where I'd probably wait for the class to be able to tell me. I think most of you could probably tell here that Iy would just be the combination of the Iy primes for the two rectangles. We wouldn't have any A dx squared term because in this instance the dx is 0. We're not both of those objects are located on the same x location as the new centroid is. So we'll do a couple examples of those later. We've also got this thing called the product of inertia. So generally speaking, it determines the degree of symmetry and can allow you to figure out what happens if you change the axis system. So basically, if you're rotating your frame of reference. One thing to note here is that if the chosen x or y axis for an object is an axis of symmetry, then the product of inertia is 0. So this is how we calculate the IXY. So the parallel axis theorem applies. So again, we can figure out what our product of inertia is kind of based upon combining a number of simple shapes like we saw earlier. So for that, one of the primary things that we're going to be using this for is figuring out what happens with a rotating frame of reference. So essentially, if you start off with this frame of reference here, that's, this is your x direction, this is your y direction, and you rotate your frame of reference somewhat, then you're going to basically get new Ix primes and Iy primes based upon the new frame of reference. And those will kind of be a combination of the original Ix's and Iys for the system that you're talking about. Ix's, Iys, and the product of inertias, your Ixy's as well. So that allows you to recalculate those parameters. just based upon what you had originally and some relatively simple trigonometry. So as we can tell here, if you start off with an initial ix and initial iy, and you rotate it and it changes somewhat based upon some sort of trigonometric relationship, then it's fairly simple to tell that at some point as you rotate, you're going to reach a point where you have maximum and minimum values for those for those parameters. So rotating the frame of reference changes it. Each cross-section is going to have a specific angle at which your Ix primes and your Iy primes are at a maximum and minimum, respectively. Anytime your Ix is at a maximum, your Iy is at a minimum, and vice versa. So these are what we refer to as the principal axes. And the moments of inertia associated with them are the principal moments of inertia. So you can find out what angle you need to rotate your thing to based upon the combination of the product of inertia and your initial moments of inertia. One thing that I think you could probably tell here is that if you have an Ixy that is equal to 0, then that means that the tan needs to be 0. Sorry, the tan of 2 times your the tan of 2 times the angle you're rotating to needs to be 0. So that's going to happen at theta is equal to 0, and it's also going to happen at theta is equal to 90 degrees. Because tan, your tan is always 0 at whatchamacallit, your tan is only going to be 0 at 0 degrees and at 180 degrees. So if you're so your tan is going to be 0 at 0 degrees, and it's going to be 0 at 180 degrees. So if we're doubling the theta p in question, then 90 times obviously doubling the 0 doesn't do a damn thing. Doubling our 90 gives us 180, and tan's 0 at 180. So what does that mean in terms of kind of our principal moments of inertia, our principal axes? That means that if we have a if our product of inertia, our Ixy, is 0, then we are already at one of the principal axes. So we already have at that particular orientation, either our Ix or our Iy is already its maximum. And if we rotate it 90 degrees, we're going to get to the other orientation at which the Ix or Iy is also, which the other one is at its maximum, and the one that was at its maximum is now going to be at its minimum. And that occurs anytime that the x-axis or the y-axis is an axis of symmetry. So that anytime you have an axis of symmetry, and anytime you have an object that is symmetrical about one of those axes, like close enough, something like that, you know that that's going to be one of the orientations at which it's at its maximum in terms of Iy or Ix. And then so that this will be used to, in this relationship here can be used to indicate what the what angle you need to rotate to, and then this will be used to actually calculate your maximum and minimums. And that is about it for the stuff you'll need to do calculations for relating to cross sections in this course.